has many different types of applications, but at the forefront are two basic rules, simply referred to as the sum and product rules, because one of them involves summation and the other one, well, it involves a product. Before we get into this or recap this, let's provide a motivating example that will set the intuition for why this makes sense, why these two rules make sense. So let's say we have a group of 100 working people, and that group is surveyed. 70% of those surveyed reported drinking coffee in the morning. And importantly here, independently of this characteristic, meaning that it doesn't matter whether or not you drink coffee. 25% of people reported listening to podcasts on their way to work. So our goal here is to maybe take this group of 100 people. So I'm going to draw my little stick figures here. They're all in a line, let's pretend. And they start at this hub. And at this hub, they're basically told to go into one of two directions. They're told to go upwards as a group if they drink coffee, and downwards if they do not drink coffee. So let's go ahead and define the set of all people who drink coffee as set D, so the set of coffee drinkers. And then, of course, D complement, D with a bar over it would mean those who are not in that set, or the complement of that set. So we know that of these 100 people that we have here, a certain percentage are going to be coffee drinkers. So of those 100, 70% or 70 would be coffee drinkers, or we would expect that, and 30 would not be coffee drinkers. Okay, so notice that we still have 100 people, right? There are no weird things happening here. People aren't disappearing. There's still 100 people. It's just some of them will migrate up and some of them will migrate down. Now, of the coffee drinkers, it doesn't matter whether or not a person is a coffee drinker. We're assuming that 25% of people report listening to podcasts. So I don't want to use P for this because that usually stands for probability. So I'll just use C, set podcast listeners. And by the way, we can say that the probability that somebody drinks coffee is 0.7. We can say that the probability that somebody is a podcast listener is going to be 0.25. And so of these coffee drinkers, once again, we'll say, hey, if you listen to podcasts on your way to work, move up again. If you do not listen to podcasts, move down. So we have 70 people here. And of those 70, we know that 25% are going to be podcast listeners. And if we take 25% of 70, well, then we get about 17.5. Now, I know that we can't have a quarter of a person or a half of a person, but I'm just going to go ahead and label this 17.5 because this could be technically could be in thousands or millions, but we'll just leave it as such. And so that means that, well, 75% of that 70, or really 70 minus 17.5, right? Because if 17.5 are podcast listeners, then the other 70 minus that are not, which would be the same thing as taking 70 times 0.75, which gives us 52.5. Okay, so barring that half a person, it's fine. And now we'll do the same thing for this group, podcast listeners, non-podcast listeners. So this branch right here will be 25% of the 30, and that comes out to 7.5. So that means that the other 22.5 would end up not listening to podcasts. Now you can see here that I can actually convert these to probabilities. And once again, if you add up 7.5 plus 52.5 plus 7.5 plus 22.5, notice that you get all your 100 people back, right? Because everybody went somewhere. We just took that one group and broke it up eventually into 4 groups. So now if we looked at the probability that somebody drinks coffee and is a podcast listener would be the 17.5 out of the 100, which would be 0.175. The probability that somebody drinks coffee and does not listen to a podcast is 52.5 out of 100, which is 0.525. Do the same thing to non-coffee drinkers and podcast listeners, 7.5 out of 100, it's 0.075. And non-coffee drinkers and non-podcast listeners would be the 22.5 out of 100, which is 0.225. Now, once again, if you sum these, the only difference is that these numbers have been divided by 100. So if you divide the total 100 by 100, you get 1.00. And notice that, once again, we have a probability distribution now. We know how every one of these 100 people can be categorized according to their two preferences. Now, we can't think about D and C as sort of being random variables in the sense that D can take on a value of, let's just say, 0 or 1. So 0 being you're not a coffee drinker and 1 being you are. And C, similar but related to the concept of podcasts. Now, notice that if what I had wanted, what I had set out to do was just to find, without drawing this tree diagram, the percentage or probability that a randomly selected person is both a coffee drinker and a podcast listener, well, let's think about what we did. We took 100, we multiplied that by 0.7 to get our 70. So this gave us our 70 right here. And then we took that 70 and we had to multiply that by 0.25. And that collectively gave us our 17.5. Well, then we had to divide by 100. And so we actually have a redundancy here because we multiplied by 100, but then divided by 100. And so notice that our 0.7 times 0.25 is really how we got the 0.175. And what is that in relation to the original probabilities? Well, it's the probability that you drink coffee times the probability that you listen to a podcast. Now, the important concept here is that really what we're doing is we're saying 25% of 70% of all of our people. So 25% of 70% of all of our people do both of these things, drink coffee and listen to podcasts. And the reason we can just multiply like this is because we have independent events. Let's say that the likelihood of listening to podcasts is much higher for people who drink coffee than it is for people who don't drink coffee. Well, then this second probability may change, and it may change to reflect the fact that we have to take into account the previous event to calculate the probability of the new event. So once again, if coffee drinkers had a higher likelihood of listening to podcasts, then the probability of listening to a podcast may be different based on whether or not you're a coffee drinker. So in that case, the way we might write this is we might say, instead of, hey, let's call this the probability of C, maybe we would call this the probability of C given the fact, that little vertical bar we call it means given some information, given the fact that the person is a coffee drinker. And so notice that it's still the probability of C, but it's the probability of C out of the people who are coffee drinkers. And this would be the probability of not listening to podcasts given that you drink coffee. And this would be the probability of listening to podcasts given that you're not a coffee drinker. And this would be the probability of that you don't listen to a podcast given or out of all the people who are not coffee drinkers. So in our case, notice that the probability of C given D and the probability of C given D bar. And what does this mean? This just means that since these are the same, it means that specifically, and we already knew that in this case, because that's how we set it up, that the likelihood of listening to a podcast is independent of whether or not you drink coffee. Okay, so we would say that in summary here that the probability of two independent events A and B occurring jointly is the probability, and this means A intersection B. You can read this symbol as and. This is the overlap between the two sets, or what percentage they share in common, and that's just the probability of A times the probability of B. The probability of two dependent events, it's the same formula, except all you're doing here is you are taking into account how B's probability changes or is affected by event A. So let me just give a quick example of that, and then we'll look at this last bullet point here. Let's just say that we know that in a box we'll have some marbles, okay, and I'll have maybe a couple purple marbles here, 3 purple marbles, and maybe 2 green marbles. And maybe what we want to know is what's the probability that you draw 2 marbles, and what we want to know is the probability that we draw basically 2 greens. And so in that case, that means that's the probability that on I'm just going to be real sloppy here, on draw 1 we get a green, so I'll just say green on the first draw, and we want a green on the second draw. Well, if you look at the probability here, it would be 2 out of 5. Right? The probability of just drawing a green is 2/5 or 0.4, and the probability of drawing a purple, I'll abbreviate that as R, is going to be 3/5 because there's 3 purple marbles in a total of 5, and that's going to be 0.6. Well, fantastic. Well, what's the probability of drawing both? Well, I don't want to multiply 2/5 by 2/5 because assuming I pull out, I take this guy and I pull it out, the probability of getting a green on my first attempt, well, that's independent because nothing's happened yet. That is going to have a probability of 2/5. But I don't want to multiply it by 2/5 because now notice that there's only 4 marbles left, and only one of them is a green. And you can see how now the probability of getting a green on the second draw, given that a green was drawn on the first draw, has to be written like this. We can't just say the probability of green because we have to say, well, what happened already so that we can calculate the updated probability. And now this would be a situation where the likelihood of drawing a green on the second draw is dependent on what was pulled on the first draw. And now, again, I can say, well, what's the probability of getting a purple next? And now, it's out of 3, so it's 100%. And so that's how we work with dependent events. Now, as far as we often call the union of events, that's the probability of A union B. That's really, we want to say, what's the probability of one or the other occurring? Okay, now in this case, we could notice, if I wanted to know what's the probability that somebody drinks coffee or listens to podcasts. Well, that actually is 3 specific events. That means just D and not C. It means not D and C. So notice that here we are, in both these situations, we are doing one or the other, drinking coffee or listening to podcasts. But an or probability allows the possibility of both, right? It's kind of like saying if you go to the motor vehicle division and you need to take care of some business, they'll say you need a form of ID, a driver's license, or say social security or passport. And so can you bring both? Can you provide both? Well, certainly, but they only need one or the other. So we do need to consider that possibility of both things happening. And if we look at where these probabilities are, we can see that we can just add 0.175. Okay, so that's doing both. Plus, here we're doing just drinking coffee, 0.525. And then finally here, plus the 0.075. Or you could just take 1 minus the 0.225, and that would give the same answer. But in general, notice that this formula says the probability of A or B is the probability of A plus the probability of B minus the probability of both. Okay, so that's slightly different formula here. Here we're just adding up the probabilities that we want, but the reason you have to consider in the union, the reason we have to subtract away the intersection, and I'll point this out, is we have to consider the fact that, let's just say here I have set A, and here I have set B, and the area of these circles and the rectangle, so the universe has a likelihood of 100%. Something is going to happen within this box. Let's say the probability of A is 0.6 and the probability of B is 0.7. And you add these together and you're like, that doesn't make sense. That's 1.3. Well, that's because when you added the probability of A, okay, the probability of A is this entire box here. And if you notice, it has covered, we've shaded an area that is also part of B. And that itself is not the problem. The problem arises now, where now if I add the probability of B to it, I have basically accounted for this region right here. This has been added in twice. And how do I account for that if it's been added in twice? Well, what is that region? That's the intersection between A and B. And so because it's possible that it's been added in twice, we subtract away the probability that both things happen in the situations that A and B are not mutually exclusive. There's some stuff that is included in both.